Tutors. Maybe. He's joking.
Well, sort of joking.
Sort of.
There have been some cases. Not with tutors, but there have been cases where people get robbed, killed. So if you're using Craigslist, just be careful. So what I want to try is, I want to try to approach this in a little different way. So we're going to talk about, we're going to finish up chapter 4. The last section of 4 is talking about equations that have fractions in them and different ways you can solve them. So let me see if I can completely freak you guys out. So, what could I do with this? Could I do anything with this? I like it. So one thing I could not do is just to do this and put a 2 there and forget about it. Right? This is not equal to this. Don't even write that down. Because what's wrong there? What's being divided by 2 here? The 4 and the 6, right? Good. So if I just do one of them, then how do the other two escape? So that can't possibly be right. You with me? So what does this really become then? This will be 4 over 2. So you just say it more directly. Say 4 is being divided by 2 and 6x is being divided by 2. There, I can rewrite it like that. Right, so this will be 2 plus 3x. Okay, so that's one little thing that you realize. Let me build on that. Some of you guys are like, how does this connect to what the hell you just said this section was about? Well, you'll see in a minute. So what if I had...
How do you get 2 plus 3?
4 over 2.
Oh.
And then 6 divided by 2 is
6
3.
divided by 2.
So once I break them up, I can try to simplify each one. So what if I had... you guys try that one. Yeah, so 8 divided by 4 plus 5x divided by 4. 8 divided by 4 is 2. And then this, you can look at this as 5 force x or 5x over 4. It's the same thing. So what would I have to multiply this whole thing by to make the fraction disappear? 4. I'd have to multiply by 4, because how did I get there? I divided by 4 to get there, right? So I have to multiply by 4 to make it disappear. And it really kind of makes sense. The only thing that has a denominator in this whole thing is there. And how do I kill that denominator? Multiply by 4. Cool. All right, so there's one little thing.
So you just write it just like that.
So one last example like this. And these are all just trying to build on an idea. So go with me on this. What you got, Jeff?
So that last one you just did, or you leave it just like that? Just leave it like 2 plus 5x over 4. That's the solution? So that's it? That's the answer for the last one?
That's just simplified, exactly. It's not an equation, it's just an expression. And it would say simplify. So I've simplified it as much as I could. So the instructions here would say simplify. So you still do this in the same exact way. The first step is the same. What's the first step? Bless you. Good. 1/2, right? 12/24 reduces to 1/2. And what's 8/24 reduced to?
X over 3.
X over 3, I like it. So, going backwards, I could do something better. I could multiply by 24. If I multiply this by 24, I'll end up with what's on top here. I'll end up with 12 plus 8x. Let's make sure that's true. And why should that work? If I multiply this thing here by 24, why should I end up with 12 plus 8x? How did I get here? I took 12 plus 8x and I divided it by 24 to get here. So if I multiply this by 24, I should get there. Is that cool? So let's see if that works. So 1/2 plus x over 3. If I multiply that by 24. What do I have to do here? What property do I have to use? Good, distributive. So 24 times 1/2 plus 24 times x over 3. You can always put a whole number over 1 when you have these other fractions running around. Just make it easier to look at. What is 1/2 of 24? 12. And what's 1/3 of 24? 8. So there's that 12 plus 8x, right? Now, is 24 the LCD of these two? What's the LCD of these two? 6. So here's an interesting question then. What if I took this expression and I multiplied by 6? Now, I might think to do that because what would I multiply this expression by to kill the 2 there? I'd multiply by 2, right? The 2 would cancel with that 2. Would it kill the 3? No. What would I have to multiply by to kill the 3? 3. But it wouldn't also multiply. So what's the lowest number I can multiply to kill both of them is going to be the LCD. So if I multiply by 6, what happens?
6.
Yeah, 6 times 1/2 plus 6 times x over 3. What's 1/2 of 6?
3.
And what's 1/3 is 6? 3 plus 2x. So I got rid of my fractions by multiplying by the LCD. So now I can take that idea. And really the idea I'm trying to get across is I wanted to show you that fractions and expressions can come from something like this. So I can undo the fractions by multiplying back by that number. So that's what we just did here. That led to this expression with fractions in it. How could I kill those fractions? If I was allowed to, I can multiply by 24 again. But then we got even better. We said, I don't have to multiply by 24. I can multiply by something smaller and make the fractions go away. Now, in general, am I allowed to just multiply out of nowhere? Probably the answer is no, the way I said the question, right? So here's the problem we're really going to see in this section. That's what I'll build up. So if I had a problem like this, let me build off that last example we did. So I'm going to show you 2 different ways to do this problem. I always have a tough time deciding on if I want to show you 2 ways or just pick one way, but I'm going to show you 2 ways on this. The first way is going to be related to what we just did. And the other way is actually the way I'm going to try to push you towards using, but you can use either way that makes sense. The worst part about that equation, of course, is the fact that there are fractions. But the fact that it's an equation allows me to do what to both sides? Anything I want to, really, almost, as long as I do it to both sides, right? So what could I do to this side to kill the fractions? Yeah, the LCD is 6. So if I multiply both sides by 6, which is completely legal because it's an equation. I can multiply both sides of an equation by 6 all day long. Here it just happens to help me. What happens? Yeah, I've got to distribute it, right? Four times 6?
24.
Cool. You guys semi with me? I mean, the whole idea of an equation is to cancel stuff out. So it kind of makes sense. If I have a bunch of fractions in there, what operation are involved in fractions? Fractions really represent division. So it should, if I multiply by the right thing, my fractions should disappear. All that division stuff should cancel. And the LCD is the one number that has all the bottoms in it. So it's the one number that can kill all of them. It's overkill, right? Because I don't need 6 to kill 2. I don't need 6 to kill 3, but I need 6 to kill both of them, right? So that's a weird assassin movie. Right. So what happens here?
3x.
Yeah, the 2 goes into 6 3, so I get 3x. 3 goes into 6 twice, so I get 2.
25.
Cool, right? And now you can solve this like normal. Does that look a lot better than the original Hell, yeah? There's no bottoms left. I killed all the bottoms. Now, I'm allowed to do this step because I said so. No, because why? Why am I allowed to do this? Multiply by 6. That's awesome I could do that because my fractions die. But can I kill every fraction I ever see my whole life?
No.
No. I can only do that here because it's part of an equation. So I got 2 sides that will keep me balanced. So you can't suddenly go home and say, Ma, I know what to do if I have 5/8 minus 1/8. I just multiply by 8. No. Right? You guys with me? 5/8 minus 1/8 is not that hard, but I can't say it suddenly is 5 minus 1 is 4. No. 5/8 minus 1/8 is not 4. How the hell did you get that much? You had 5/8 minus 1/8 is 4. Whoa. You guys see what I'm saying though? So the only reason I'm allowed to kill these fractions is the fact that there are 2 sides that will balance each other out. So how do you finish this equation out? Yeah, subtract the 2.
22. Well, divide by 3.
Divide by 3. Now does 3 go to 22?
7 minus
Yeah, so you can say 22 thirds or...
7.
Yeah, either way. If I don't say it, you can put it either way. You guys with me? Some of you guys had some trouble on that first page of the test. There was a problem where the answer came out as a fraction. And some of you guys said undefined or does not exist. A fraction's a number, right? In fact, I should be surprised if I solve an equation from the real world and it comes out to a nice answer. That would be like, what? I expect 4.962 or something freaky. So now this opens the door. We're going to have equations that you can solve and they'll come out to be fractions at the end because that's closer to real life. You're not always going to get pretty answers at the end. Do I care that I got a fraction at the end? No, because I'm done, right? That's a great place to get a fraction, when you're done. So don't let that freak you out. That's just the answer. Okay, so you guys try this one. Oh, Jesus. Oh, it'll come out nice. This will actually come out nice. Anybody else not get their test back? Yeah, there's 3 fractions up there, but it's not that bad because the LCD for 8 and 3 would be 24, and 12 flows right along with that. So the LCD here is 24. If you really wanted to, you could always do 2 times 2 times 2, that's a 3, and this is 3 times 2 times 2, and you can just give whoever's missing whatever. But don't automatically do that. You might be able to just kind of look at it and tell what the LCD is. Oh, and I forgot to show you the other way. So I'll show you the other way on this one. So we'll do it the same way we did that one, and then I'll show you a different way to do it. And you can pick which way you like better. Yeah.
You have to find the LCD of all 3 denominators.
Exactly. You want to kill all of your denominators, right? You want the next step to have no fractions left in it. And the LCD is the only thing that can kill everything, because it's the only number that will have all of these in it at once. Does that make sense? That's in fact the whole idea of LCD. That's why the approach we take works. You give everybody what they're missing relative to everybody else, so everybody is represented in the LCD. It's got everybody in it, so it can kill everybody. So if you multiply by 24, and really I kind of cut to the chase. I just put 24 next to each piece, just to do that distribution at the same time. Does that make sense? And now you can kind of attack it a little bit quicker. 8 goes into 24. So I get 3x. 3 goes into 24. 16. Good. See everybody with me? Because we are multiplying by that. So whatever's left over gets multiplied by whatever's there. 10. That looks a lot better. All right, 1 step, and there's no fractions left.
I'm sorry. How did the denominator go away again?
Just the fact 8 goes into 24 3 times. So there's a 3 there and there's a 1 there. So if I had 24 over 1 times 1 over 8, how does that reduce?
1.
Yeah, 1 and 3, right? You with me? That cross reducing?
It says yeah, 24 times.
So
Did it
8
come in the denominator? Okay.
goes into 24 how many times?
3.
3. That's all. So 24 divided by 8 is 3. 24 divided by 3 is 8. 24 divided by 12 is 2. So the bottom's not there anymore because it went together with the 24 to make that new number. Right? So it canceled. That bottom canceled. Every time the bottom cancels with 24 leaves you 3. The bottom cancels with 24 to leave you 8. 8 times 2 is 16. The bottom cancels with 24 to leave you 2 times 5 is 10. And you're guaranteed that's going to happen as long as you use the LCD. Because the LCD will exactly cancel every one of those because every one of those is in it. Okay, maybe. You might like the other method better. And then how do you finish this out?
Minus 16.
Minus 6.
Divide by 3.
Negative.
Cool. Of course, you can realize that checking your answers here is going to suck a lot more. Because you have to put them back in the original problem. So you end up with these fractions. Yeah.
Do we have like the LCD for the 3 of them or just
You want the LCD for all 3.
so we have to for all 3?
Because if you don't get the LCD for all of them, if you multiply by 12, for example, will 12 cancel the whole 8? No, it's going to leave something down there. You don't want any fractions left. You want to kill all your fractions. So let me do the same problem again another way. So if you like this way, sweet. If the other way makes sense too, even better.
What if the denominator on one of them is already prime?
Like the 3 is prime. Right? 3 is prime. So I just had to make sure that my LCD had 3 in it. So if I had an 11 down here, my LCD has to have at least 11 in it. And anything else it needs to cover those guys. Does that make sense? So again, any way that I normally find LCD, I'm still going to use that exact same method here. Finding the LCD is by itself a problem that I could use anywhere I need. The LCD will make things easier. the most common place to use it is when you're adding and subtracting fractions. But now we're realizing it actually works with killing fractions in an equation. There's a whole other purpose to find it. Okay, so let me do this problem a different way. Okay. So this still requires you to know what the LCD is. So the LCD is 24. I'm thinking that some of you guys might like this way better.
It's easier?
To me, it's easier. It's the way I like better. And it makes future stuff easier. So that's why I want to push you guys in the direction of this. But this is kind of showing you more what's really going on. This one is an easier way of doing the same thing. So let's see what you guys think. How do I give everybody that LCD? What's this guy need? 3. So you multiply by 3. What's this guy need? 8. We good so far? I mean, this should be old news. We can make everybody have the same LCD. And of course, he needs a 2. So then you get 3x over 24 plus
16 over 24.
equals 10 over 24. And now what do you multiply both sides by to kill? Yeah, you multiply by 24. But now it's a little easier to look at, right? Die. And what are you left with? 3x plus 16.
10.
Same thing we had there, right? So I show both ways because normally about half the people like that way better and half the people like that way better. So whichever way you like better is the way to go. And I'll tell you this, like I said earlier, I wanted to show you this way first because it kind of shows really all the math of what's going on. But this way is a lot closer to what you have to do with fractions anyway. And this way will help the day that you get to when you have problems like this. Oh, shit. This way will make that stuff much easier. Right now, of course, that's like, I don't want to be there. But that's coming. That's math. That's actually math 90. And of course, it comes out again in math 110, 103. And is everybody cool? I mean, that would just solve the same way. It's the same. We got to the same place. It's solved the same way. So whichever way you like better is the way you can do these kind of problems. So let me show you a more specific situation. And this is something I saw some of you guys doing already on the test. There is only one place that you can cross multiply and have it make direct sense. It can be used to as a shortcut, but you got to really understand how to use it. There's only one place where you can directly use this. Have anybody ever heard cross multiply before? Some of you have, because you used it in the wrong place on the test. So here's the idea behind cross multiplying. I'm going to show you, I'm going to say this, and somebody's going to forget I said this. I'm going to show you why it works. But so what I'm about to do is a lot longer than it has to be. But I'm showing you why it works. Because I know somebody's going to go, what are you doing all that? What would the LCD be between these two? 55. So if you multiply, let me do this a little different way. If you multiply this by 5, doesn't that go away?
Yeah.
And if you multiply both by 11, doesn't that go away? So didn't I really multiply by 55 on both sides? You with me? Let me just let you absorb that for a second. So what do I get on the side then? What's left alive there? 5x. So what did the 5 really look like it did? It looked like it just came up here. Now be careful. In mathematics, you have what it looks like it does, and then you have the reason it does that. Right? So this is the one place that the method we use to solve it will make it look like you cross multiply. That's where the word comes from. Cross multiply. 5 times x is 5x. 11 times 3, see that's what I would do, right? 11 times 3, 33. So when you have a fraction equals a fraction, that's the one place you're allowed to cross multiply. Cool. And then, of course, the last step.
Do I?
So you can write that, or cool, either way. Have it improper or mixed. If I don't say, you can give it to me either way. Is that cool? Okay, good. But when you have a problem like this, now why won't that work the same way this did? Well, because it's got two things on one side and one thing. Well, who goes to what? Then no. So that is a shortcut to this when I have only one fraction on each side.
We need more of that.
Say again?
We need more of that.
You'll get some of those.
No.
Look, you want to see more to understand, or you just want more of that on the test? Oh, so here's here's what it would look like just straight up, not explaining it really, just doing the problem. So if I had 8 over 7 equals 11 over x. So the shortcut now, here's why it works. But the shortcut is whatever's there ends up there. Whatever's there ends up there. So x times 8, 8x equals 7 times 11, 77. It's a shortcut. And shortcuts are always
good, the best, but dangerous.
No, exactly. They're dangerous because you remember the shortcut, but you forget why it works, and then you start using it in way too many places because, well, if it works there, it's got to work here. It's fractions here too. No, too bad. So you got to always be able to explain why a shortcut works. So here, I would multiply both sides by x. So you kill the x. Is that cool? So that would die there. Is that cool? You guys see that? So multiply both sides by x, so it ends up there. See? So it looks like it just went up there. And then if I multiply both sides by 7, it would end up up there. So that's the shortcut. Is just go ahead, screw that, just go ahead and bring them up to the opposite side. Yeah.
I'm trying to understand, when will we use this though? That's kind of like...
When would you use this? When you have an equation that has a fraction equals a fraction.
So is this like, does it tie into the other problems we've been doing, like the LCD or no? Kind of?
It ties in because it's an equation with fractions in it. The nice thing is, if you have one fraction equals one fraction, here is a shortcut way to solve it. Now, if I have fraction plus fraction equals fraction, I can't use this directly. Right? It's not the right form to use this shortcut. You guys with me? Okay, maybe. Again, let me look at this problem again. This might get a little freaky, but let's see. Can anybody tell me what the LCD is between those two?
7x.
I love it. It's 7x, right? So what happens if I do the same thing we were doing earlier? Multiply both sides by 7x.
Oh, I get it.
What happens? 7 cancels, so the x just effectively came there. Here, x cancels, so the 7 just effectively came up there. So it's the same procedure, but there is a shortcut because the problem is simpler. I like it.
I get it.
Sweet. Okay. So you guys try these two.
It's like this problem here, the 3x. 3x. We would cross multiply that
That looks gross. All right. I call that. That's a good first step. 20 times 3. And then subtract a couple 3's because you only want 18. 20 times 3 is 60. Minus a couple 3's is 6. So that'd be 2.
Right.
Good. I love it. And then one step when you're effectively done, but you might have to do something with that fraction. One more step and you're almost done. I like that. So one more step and then there's one more step. Except for the LCD is not 5x. This is what happened. So we multiply by, so on the board I kind of showed you can multiply by 7x because the LCD would be 7x. Here the LCD would be 15x. But I want us to start, so that would be why it works, what we do. Here's what we do. They do, so that's why they show up over here, right? So if the x's cancel here, they don't cancel there. So it looks like, so watch. So the reason it works, so here's the shortcut. The shortcut would say this x would just go up there, and the 7 would just go up there. Now why does that work? Because if I did multiply by the LCD, 7x, the x would cancel here, the 7 would cancel there. So see how the x just came up there, and the 7 looks like it just came up there. So if you do multiply by the LCD, whatever's on the bottom on that side cancels, and it picks up the other dude. So it looks like that guy just came over there. It's like that 7 just came over there. So here, you just can do 3 times 18 equals 5x times 2. That's the shortcut.
So there's no 15.
So the long cut would be LCD multiplied by the LCD. Right?
But this way you're saying
There's a shortcut to it.
that times that.
Yeah, so multiply 5x times 2. Multiply 3 by 18. That's the shortcut. And the reason it works, you can show why it works by using 15x and then seeing what cancels. So be really careful about what you're actually going to do versus why what you're doing works. You don't want to mix those up too much.
So you're doing a cross. It's still going to cause like a fraction though, right?
Nope. Because you're going to have one goes up equals, the other one goes up. So both bottoms go up to the other side. Oh yeah, just reduce it. I love it. Cool. Or you can do it as a mixed number. Yeah. Be careful here, it's a little minus. I know some of you guys are just starting the second one, but let's look at the first one real quick. Make sure we're on the right track. Now let me do it, and then I want to remind you why what we do works. So what would the shortcut say to do? Yeah, 3 times 18 equals 5x times 2, 10x, cool. And then how do you solve that equation? And what's the one thing you definitely have to do with this? Good. So at least make it 27/5. And of course you can have your answer or as
5 over 10.
2/5.
yeah, you guys didn't reduce yet. So reduce somewhere, right? 5 and 4/10 reduces to 5 and 2/5, right? Good. So if you don't reduce it, you will lose points. If I don't say to have a certain form for the answer, either form is fine. But I don't have to tell you to reduce. That's just always there, right? Reducing is just a part of the whole thing. Now, the reason that works, just to remind you guys, because this is important to understand why it works. what is the LCD between these two?
15x.
15.
Good, 5x and 3, 15x. Good, the 3 and the 5 would be 15, and the LCD needs an x in it too. There's an x there, so it's 15x. So if I multiply both sides by 15x, what happens here?
Comes.
5x, which is that. So that looks like it just comes up here. Right? You guys with me? So it looks like that 5x just came up there. And what happens here? X is canceled, 5 goes into 15, 3 times, which is what was there. So it looks like the 3 just comes up there. Does it actually do that? No, but I can use it as a shortcut. So the shortcut would be just take the bottoms and take them up to the other sides. That's why they call it cross multiply. And that's the one place it works directly. You could use it as shortcuts in other places, but you have to know how to adjust it. This is the one place you can use it for sure.
How'd you get the 27?
Oh, 54 tenths if you divide by 2. 54 divided by 2 is 27.
Why are you dividing by 2?
Because I can. Remember, if I end up with a fractional answer, I have to reduce it if I can. Good. I like it. So it's not a part of the problem, it's a part of the idea of fractions. If I have a fraction, I reduce it. I don't want to give you a non-reduced fractional answer. It's got to be reduced. Okay. So finish this one out. I know a few of you guys just started that one. Just be sure you can't do the same thing we did here. Right?
Do we start using the practice book again?
Yeah. Good.
Good. Look here. That's all I can do. LCD is
Yeah, I love it.
That's your.
It's not going to be anything pretty at the end. Trying to figure out how many points you'll get if you only do so much. What's that all about? So LCD here, like you said, is 30.
Yeah.
So how do I solve this and what do I use it for?
Multiply both sides by 30.
Yeah, multiply everything by 30. And you can put it over 1 just to make it look better. Yeah. And then what happens here?
That's the first way, right?
Yeah.
10
10.
is minus 2.
So 10 times 2x, 20x. Is that cool?
Yes.
15 goes into 30 twice. 2 times 1, 2. Good. 30 goes away, so you're just left with x. I like it. And now, don't worry if it looks like it's going to come out ugly. Just do what you know you got to do. Let the math happen. You don't try to say, oh, it's going to come out ugly. I must have made a mistake. No. What's in the wrong place?
28.
So what do I do?
Minus 22.
Yes, die. So then I get negative 2 equals
19. Negative
Negative 19x, get different signs. So you got to subtract. And then the last step.
X
Over 2.
Careful.
19.
What do you divide by?
19.
9.
Negative 19.
Negative 19.
You with me? What do you want to get rid of? Whatever's with the x. End of story, right? This is actually good because it reminds me of a problem on the test that we had a lot of trouble with. That goes away. What happens over on this side?
2 over 19.
Yeah, these cancels. You get 2 over 19.
That's what I got.
Cool. So there was a problem on the test, and I did this on purpose. I had something like 14x equals 7. And I always get somebody, they don't show any work maybe, and they say x is 2. Or they do show some work and they do this, and their answer is x is 2. But I say, follow the work you just did. Where's the work you just did? Where does it take you? 14 divided by 7 is 2x equals 1. Right? So you're not done then. So if you would have taken that last step, I would have been okay with it. It would have been twice as many steps you should. It should be a one-step problem, really. But now you have to divide by 2. The real way to solve this problem, you don't let the numbers tell you what to do. They're stupid numbers. We are humans. We created the damn numbers, right? So we tell the equation what we need to have happen. And what is it we don't like? What number is in the wrong place? 14. I want to make x by itself. Screw whatever number's over there. I don't care. I want to get rid of whatever's with the x. So this is somebody letting the numbers tell them what to do. Don't be that person. You know you got to divide by 14. You also know, and the reason you don't do it is because you kind of know ahead of time, that ain't going to work. That's not going to go in evenly. But I don't care. The answer to an equation could be anything. Doesn't have to be pretty. So here I get x equals
1 over 2.
1/2. There's that one-step problem that it should be. We saw that kind of happen over on this problem too. Whatever's there, you divide by. You want your x by itself. Cool. We're going to do that here in a minute. So any questions on those? Yeah.
If it's negative 2 over negative 19, how many answers not negative?
Because the negatives will do what? Cancel. So negatives can only survive if there's an odd number of them. Here there's 2 of them in there. They're going to kill each other. Yeah.
But can you keep it?
Oh, good. Oh, that's good. What's up?
I'm still coming out with, like, okay, on the second step where you had, okay, where it has 10 over 1. Oh, it's 10 over 1, is that right? No, 30 over 1.
Yeah.
So then,
So let's do this the other way. Because again, I think viewers are going to like this way better. It's actually better for us in the long run. The other way says, make everything the LCD and then kill them. And very often it's easier to see because we're used to building LCDs. So I know the LCD is 30. You got to know that either way you do it. How do I make this first thing become over 30?
10.
Multiply by 10. How do I make this guy become over 30? Times 2. This guy is there, right? So then I get what here? 20x over 30 minus 2 over 30. So now if I multiply by 30, they all cancel, right? So then I get 20x minus 2 equals x, the same way I got there. So either way you like it. I want to show you both ways, really, because I'm not teaching 103 or 110 next semester, or 90, really. So I don't know who you're going to end up with.
can we get it?
And they might have one way that they only do it that way. So if I don't show you both ways, you're screwed. So I want to show you both ways. What's up? Okay. And I was going to talk about who's teaching 90 next semester, but nobody reminded me to bring the schedule, so I didn't. So, Hopefully I'll do it Thursday if somebody reminds me. Oh, I do remember. I did look at it. Jenny Van den Einden. You guys know that name? Jenny Van den Einden. So it's a hyphenated last name. She used to be our department chair.
Is it just next semester? Or
I know she's real skinny, dark hair.
She is teaching a Math 90 next semester. So, huh?
When are you?
Not next semester. And we haven't set the schedule for the following year yet. So, I think Nemi Capacia, I don't know if you guys know that name at all.
She does everything.
Nemi Capacia, she's teaching a 90. I think Arturo Milan is teaching a 90 also. So I don't see anybody writing. So in case you're curious, those are three right off the top of my head that I can remember that I would suggest would be good to take.
All hers on the computer.
Sometimes. If she's doing the large lecture, there's large lecture classes that you meet one day in the classroom with 100 people, and then you split up into groups and you go the other day of the week you go to the Math Study Center where they have the computers, and you do homework on the computers, and the teacher kind of goes around the room. That's the large lecture class. That's the one where you see like 3 sections in a row. They all meet in the same room, and they all have a cap of 45, and you're like, what does that mean? That's because they're going to fit all the students in one classroom. It's the large lecture. Right. So if you think, now of course you guys probably haven't had much with online homework systems. So there'd be no way for you to know if that's good or not for you. But that's another way that we present that class. It's called a hybrid class because it's partially lecture, partially on the computer. Okay,
What
cool.
was that first name of the teacher you said?
It's Jenny Van den Einden. It's a hyphenated last name.
How do you spell that? How do you spell his last name?
Van
Yeah.
Den EYN.
Just say it into your
Den. You can't miss. She's the only one with a name near that.
Okay.
And then Nemi Capacia
Okay.
and Arturo Milan. Those are the ones.
Nanny?
Nemi.
Never.
Nemi.
Nemi.
Nemi. N-E-M-I-E.
What chapter is this?
N-E-M-I-E.
Chapters. He's saying
Oh, wait,
do math.
Sound like Never.
Two.
Got nerves.
Okay.
Wait. 2, -2 divided by...
So I just promised you guys I'd say some suggestions on who to take next semester, because obviously if I was in the class I'd be worried about who am I going to take the following semester. And I'm not sure which way those guys teach this. So let me give you one more example of this before we get into chapter 5.
Jenny Van den Oh, there we go. She's writing it down.
Oh.
I bet
Ay,
you
ay,
she's
ay.
Yeah.
Then,
Yeah, I'm sure.
then, it's a girl. Nini Capacia.
Arturo. The last guy's Arturo.
It's Arturo, Million?
Arturo Milan. Yes.
Oh.
So he's the dude. And Nemi is not a cartoon character, she's a person. Yes.
Hybrid class going on next semester? Like 90?
Arturo, I can't remember, to tell you honestly, but I saw that he was teaching it. So I'm just telling you what I can remember when I looked at the schedule real quick, the teachers that were teaching it.
You will bring, why are you transferring or what's it?
So again,
Are you transferring?
What are
I'm
you
just
gonna
not
teach?
teaching a 90.
What are you going to teach?
Do you teach 110?
I'm teaching a 160, an 88, and a 180.
Alright, I got you. 180. So you have to find these.
All right. So what do you guys? What about this one here?
We'll just bring our work to you.
So you have to find these.
Come
No.
to your office.
What do you guys think about this problem here? This is a little bit different, and this is where people make a big mistake, because a few of the problems in here, a few of the numbers in here are not fractions. But there's one big point to make here. If you multiply one side by something, you must multiply the other side by something, which really translates into nobody can escape. But what people end up doing is, so for example, if you want to do it the first way, what's the LCD of all the fractions that are in there?
15.
Beautiful, because these are not fractions, right? So LCD is 15. The biggest mistake I'll see is somebody will do this, 15, 15, and then I'll tell them you made a mistake, and they'll say, what do you mean? Those are the only fractions in there. Why would I multiply the other two? And it's because you don't get a choice. If you multiply one side by 15, you have to multiply the other side by 15. It's the whole idea of nobody can escape, right? So really, if I do this, 3 minus 2 is equal to 5 minus 4. Is that true?
No.
Think about it.
Yes.
Okay. See, so it's good to think first. 3 minus 2 is 1. 5 minus 4 is 1. Now, if I multiply by 15, if I only multiply pieces of this by 15, 15 times 3 is 45. 15 times 5 is 75. Is that still true? 45 minus 2 is 43. 75 minus 4 is 71. That's no longer true. Are you with me? You guys semi with me? Because really, that's the same thing as the mistake I make if I only multiply these pieces. So the right way to do it is to multiply the whole thing by 15. So this would be 45 minus 30 equals 75 minus 60. Is that true? They're both 15, right? So as long as you multiply every piece of the problem, it maintains the equality. It keeps that equation true. Obviously, this must be a big mistake, and that's why I keep going about it. Right, so don't focus just on your fractions. Whatever you want to do to make something happen, you got to do it to everybody. That's the rule. You can't just pick and choose. So if I do multiply by...
Because the 2 and the 4 do have a 1 underneath.
Exactly. They still are.
They are fractions.
Ratios. I just don't see the bottom, and people think, I don't need to do those. They don't have a bottom. When you're saying, of course they got a bottom. They got 1 on the bottom. So what happens here?
3.
Good. 5 goes into 15. 3, so I get 3x.
15.
Yeah. 15 times 2.
15.
30.
3, 5. 5x.
Good. 3 goes into 15, 5, so 5x. 60.
30. 15 times 2 is 30.
So now which way you want to go? What do you want to do? With your x's, let me be real good. Whatever personal choices you make in life is your own thing. But what do you want to subtract or add?
Add 30.
And it's not wrong to minus 5x, but remember I always try to stay away from bringing negatives in when I don't have to.
Say positive.
You don't want to add 3, that sucks.
Minus 30.
Yeah, minus 3.
Oh.
Because I want this to go away. So then I get negative 30 equals 2x.
Wait a minute. You said stay away from the negative.
Exactly. If I would have subtracted 5x, I would have gotten a negative 2x. But if I subtract 3x, I end up with a positive 2x. I stayed away from the negatives. The other numbers I got no control over. They're negative. What can I do about it? But, what do I want to do next? I don't want to add 30.
Why?
What number's in the wrong place? 60's in the wrong place. It's there, right? I only want x's on that side. I want to add 60. No?
30. That's 30.
Positive 30. Big one's positive.
Oh.
Yeah, divide by 2.
15. So x.
X equals 15. Cool. Yes, ma'am.
I know going all the way back to the beginning, but, so you said that 2 and 4 cannot be used to find the LCD because they're not fractions.
LCD means lowest common denominator. So like Jacinda pointed out, the 2 and the 4 actually have what in the denominator?
1.
Yeah. So they are represented in 15, but 1 doesn't really add anything. But the problem is when people try to use 2 and 4 in the LCD, that doesn't make any sense. They're the numerators.
Oh.
Yeah, so a whole number is always a numerator because any whole number is automatically over 1. So they shouldn't be taken into consideration for LCD.
And it wouldn't make sense to use for 1 because it doesn't
Yeah, we use 1 automatically. It doesn't change. 1 times 15 is still 15. Good. Okay. So I want to do something real quick, and then I want to let you guys do a few problems out of the blue booklet, blue notebook. Chapter 4 was all about fractions, so not too surprisingly, chapter 5 is all about decimals, right, which fractions leads into. And decimals are really just specific fractions. In fact, what number is our numbering system? What number is it based on? So when I write the number 4820, what does that mean? Thousands, right? So our numbering system is based on 10. Because we have 10 fingers, really, is the best theory going. Right? Makes sense. If we had 8 fingers, we'd have somehow, well, not our thumbs, we have to evolve. If we had 8 fingers, we'd somehow have a number system based on 8. That's actually what I teach in Math 120. It's different number systems. So now, today we're going to, so we know that's 1,000. We know that's the hundredths place, tens place, ones place. Every time I take a step down in place, what happens to the number that represents that place? From 1,000 to 100 to 10 to 1. It loses 0. What's a better, more mathematical way of saying that same thing? How do you lose a 0 when you
Increase
Place value.
when you divide by 10? Right? 1,000 divided by 10 is 100. 100 divided by 10 is 10. 10 divided by 10 is... So the next place should be, take 1 and divide it by 10. So that next place is the tenths place. So that same idea applies. I mean, that's our number system is based on that very simple idea. If you're in a place, the next place down is that place divided by 10. So if I'm in the 10,000ths place, the next place down is the thousands place. Divide that by 10. Hundreds, tens, ones. Keep going. Our system doesn't care where we are in a number. I divide wherever I was by 10 for the next spot. Are you guys semi with me? Now, I don't know if you've ever heard it explained that way, and I know a lot of you should already know that that's the tenths place. But that's really why. So what's the next place? Hundredths. So really the number associated with these, 1/10, that's the tenths. That's why we call it the tenth, because that's 1/10. It's the hundredths because that would be 1 over 100. You guys with me so far? So far so good? So how would you say 0.7 itself in words? Don't say 0.7. How else would you say it better? What would it look like as a fraction? Let's start there. 7 over 10. I love it. So then how would you say it in words? 7.7. No, get out of here. Let me do exactly what he just said not to. Let's see how that works out. So 7 tenths. It's normally a bad idea. You guys still kind of with me? So what if I had this number? What would that look like as a fraction? How do you find what place I'm in? You know, how do you get 1,000? Tenths, hundredths, thousands. I like it. So that's 4 thousandths. So in words, 4 thousandths. You have to have that THS. That's important. If you don't have a THS, if you have an S, I'm thinking you mean 4,000. No, you mean 4 thousandths. You mean something really tiny, right? Not 4,000. Okay. Semi with me? So how would you say this number here? What is that number? What would that look like as a fraction? I got a lot of things coming at me. I like that. So it's 2 and 1 hundredths. Right? It's a whole part and a fractional part. So it's a mixed number. It's almost like the definition of mixed number. You get a whole piece and a fractional piece. Right? Yeah. So it's 2 and 100ths. In fact, think about how you write checks. We've all experienced this. How do you write a check? If you wanted to say, I'm going to pay you $789.92. You say exactly what I just said. You say 70. You better be happy I don't make it. Checks out. 78. And, right? And then you even make that into a fraction, 9200ths. Right? And is the decimal place. So you never want to say and unless it's the decimal place. You wouldn't say $4,127 and no. There's too many ands. It's like, how do you have two decimal places? So you have to be very specific when you're going from math to English. The and means decimal place. So don't have too many ands running around. You're like, how the hell did you do 5 decimal places in your number? Is that semi-cool? Or understood? Okay. So let's try this. Let me see what you guys think about this. This is page 50 in your little workbook that I know we haven't used in a while.
Come on, yeah.
Let me see if they even have this thing. Well, I have to turn off.
Page 80?
50.
50?
Page 50, yeah.
Oh, I didn't get 80.
You're out of 30.
Yeah, so let's do the even ones out of what you can see here. I don't know if you all brought your books.
What?
Do the even ones. Do 2, 4, 6, 8.
Oh, they. We have to write it out, or we gotta.
I think it says in words, right?
Yep, just like we did here.
So this is, so here, this is the 10. Wait,
But if you need to write it as a fraction first, you always can. As long as you end up with it in words. So you can do just like we did up here.
so would you go 3 and 6? 21.
You don't round it. Yep.
Wait, 3 and 6.
This way, though, right?
Beautiful. Let's kick ass.
I would say, yeah. I agree.
So number 2, real quick. What place is the last number in? Thousands. So how would you say this? 3 and 621 thousands.
600?
3, it's a whole number, right? And 621 thousands. Because what would that look like as a fraction? What would it look like as a fraction?
100, 3 and 600.
Or 621 over
3
1,000.
and 600.
But either way, it's 6.
So if you write it as a fraction, you actually just say the fraction in English now. 3 and 621 thousandths. Don't say over thousands. Right? Say thousandths.
3 and 600.
If we said 621,
Yeah, but don't put the and. That's what I was saying earlier.
Uh-huh.
When you say and, that should only mean your decimal.
And
Yep.
600. 21
and 600.
Over
Good.
The TH on the right.
THS. Now, real quick, humor me for a second, because you guys somebody might be thinking this way. All right. So I know I always show a lot of math associated with what seems like very basic things, and this should be very basic. But some of you guys might be thinking to yourself, that's 6 by itself. What place is that 6 in? It's in the 10th spot. What place is that 2 in? 100th spot. So why the hell does the whole thing get called the thousands then? Right? Because the last thing's in the 1000th spot. But these two are not in the 1000th spot, right? So let's really analyze what this really is. Go with me for a second. Or don't, just pretend you are. Guys,
Writing all their place values.
Isn't that 600 plus 20 plus 1 all over 1,000? You with me?
Yeah.
So what happens here? Isn't that 6/10? Like you know it's supposed to be? And that's going to be 200s like you know it's supposed to be, and that's going to be 1,000 like you know it's supposed to be. So that's why it works, to always look at the last number, and wherever that guy is the way you say it. Right? So if I had 0.4759, that would be 4,759 10,000s, tens, hundreds, thousands, 10,000s. I love it. So you always go by the last number in there, because the rest of them would still work if you expanded it. So the last number rules the day. He's the one that's going to see, what word do I use? Okay, keep going. Yes, 1,500s.
I have 2
This was right in fraction form?
Yeah, that's what they mean by standard form. Put them in, not fraction form, decimal form. Yeah. This one will be where you put it in fraction form. So there's no and, right? So the 5 should end up in the 10,000. So it'll appear that 1 was in the thousand spot, so we called it thousands, right? So now going backwards, if they call it 10,000s, that must mean the 5 is in the 10,000 spot. So where's the 10,000 spot? So this is the tens. So that would be 10,000s, right? Just keep going. Tens, hundreds, thousands, 10,000s. Hundred thousands. You just keep, you're like dividing by 10 more, 10 more. So you keep multiplying the bottom by 10. So it starts off with 1/10. Then the next spot would be times the tens, so 100s, 1,000s, and 10,000s. So where's that 5 gotta be? In the 10,000 spot. So where's the 10,000 spot? So the 5's gotta be there. So it goes there. And what goes here? 0.
So the end is
to
like
keep that spot.
Right, and then erase
Oops,
it,
sorry.
and 46 and
Oh.
400, yeah.
and
So this one, put it purely
But
decimal
You
form,
don't,
no
and
fractional piece.
you don't put.
So you don't need that.
No.
So that would be
I just have
1700.
one. Oh.
That's what that means. If I
Because
put
right
both
here,
of them there,
36.
it's kind of like hundreds.
But you
So
don't
just,
have.
I want it purely decimal form. This is close, but where's
Oh.
the 5? What place is the 5 is? Tens,
1,000.
hundreds,
Go
thousands,
36.
10,000s, hundred
Get rid of that
thousands.
end, 100.
It's supposed to be in the 10,000s. So we put it too far out.
I think so. 1,000.
I like
We
it.
take this.
Oh.
Right, because we have 2
36.
ends.
And 400 1,000s. I love it. Because another and would be another decimal
Another
spot.
decimal.
And that would
Come
freak
on.
the math out.
Because I'm
That
going
was
to
beautiful.
the 10.
That's it. 400, 7. Good. And then 30%. So the tens, hundreds, thousands, 10,000s. Beautiful. Yeah.
Oh, and numbers.
So that, okay, yeah.
It says, in the simplest form.
So maybe this will help me.
Could be.
It's almost like, can you spell it? Like,
But they do it, right? They spell it? Or what is
No,
it?
she's like, she'll say 1, 1, 2,
Oh, okay,
0,
okay.
point, you know?
And you could just say, I just want to make sure I hear you right.
Yeah.
It's got a bad line. But now you don't have to do that. Hopefully, after this chapter.
I wrote that after this. I know it's not, it's funny, but it's not funny.
So number 4, how'd that go? Once we talk about number 2, number 4 should have been pretty easy, right? Yeah, 36 and 401 thousands. I love it. So be careful about putting another, don't say 401 thousands, because that and would be another decimal spot, which would freak math out. What about this one? This is going backwards. It's basically this just backwards, right? So they give it to you. That's what they mean by standard form, just a decimal form, right? 407, okay, and, all right, so that's a whole number, 407. Hopefully it's going to come out because they turned this thing in a weird place. 1700s. So I know I want 17, but I want that 7 to end up in this spot. So it's all about that last number. It's what rules the day with the word I use and the word that they gave me. So here's the tenths, hundredths. I want that 7 here. Bam. So that's 1700ths. So I look at that like a little hangman game. You put the spot in, and then you put the last number in the right spot. 8's a little bit freakier. Now, does 8 have a whole number part? No, I don't see any and, right? So this is all decimal, right? 35 10,000ths. So then I go tenths, hundreds, thousands, 10,000ths. So I found my spot. What number's got to go in that last spot? The 5, the last. So it's 5, 3. There's my 35. What's got to go here?
Zero.
Those are placeholder zeros. So those zeros just kind of show me how far out I go. So I think I said this already. The Babylonians didn't have a symbol for 0, so they just had to do a lot of guessing. And it's not really far from the truth. So thank God we have the idea of 0. So what about this next spot? That's the last piece we haven't done yet, which is really going from decimal to fraction. So try those. 10, 12, 14. Be careful, it does say, as always, whenever you end up with a fractional answer, you gotta make sure it's reduced. completely take your decimals out. It shouldn't show up anymore at all. So that's what's good. 10 and 5 tenths. Be careful how you reduce 5 tenths. Good. And then this one, this beautiful one, there we go. Purely a fraction or purely decimal?
Because this is before the brain.
Got it.
Correct. This is before
Yeah, that's a good first step.
and the point
Good. And then simple forms. So each one of those can reduce.
like tens,
You just reduce each one.
hundred.
Something will go into both 8 and 100. So reduce it by 10. Seems to reduce it, so you can divide this one by 5 on the top side.
Okay, and then this one?
Don't worry about that section, we haven't got it.
Zero, 5, just over 5.
I don't see.
Number 7.
Yeah, got it. Yeah.
Nine,
I'm thinking that.
210. So you go, let's say, your point, tens, hundreds, thousands, 10,000s, right? Or it's
That's how I understand it.
Number 7?
That's how I understand it. Right.
Right.
Oh,
Man, this is gonna be
202,000.
different.
Okay, all right, now makes sense. So I want to get to the thousands spot. So tens, hundreds, thousands. And then I want to put the last number in the thousands at 2. Oh, 2, and then that fills up all my spots. Does that make sense? So I don't know why I'm saying
Like, how you go negative, like -2 is smaller than -1, you know? Is it that same kind of thing?
202, I want to put
I think so.
the last number
Okay, you
2.
know what? I said,
The next 202, and there's no other things to fill with 0, so
because this is a 10.
Right,
that
right,
last number
right.
goes in this place that it
Okay,
sets.
and then
So it said
how about
thousands,
this
so I
one
gotta
then?
put that
Because these were
202, that
half the
2's gotta
same.
go in the last spot.
Yeah, it's
Same amount.
different than real life.
Oh,
Hey, think about it.
So maybe that's not right.
that's what I'm
I
wondering.
got confused with the other one. It said 200. I thought about 1,000.
But it,
Oh,
because a 10 is
Oh, but
bigger,
maybe
because a 10 is bigger than a 10.
It's like
one's
Well, it's
10,
1780. Yeah, so it's not, it's not
One's
1700.
10.
The other way to say that is
He was, remember he was
1700.
saying to me,
Yeah,
Right?
a 10
This is not the same idea, this is 1700s. So,
But you don't see it.
1700 I can break up in a different way because 17 is bigger than 10. So 1700,
This is the one place.
I could break up in another
In other words,
way.
it takes.
So the only way you can break it up would be 10 plus 7 over 100. So it's 110 plus 700. But it's not easy to say that.
Yeah.
Right? So with whole numbers, it's easier to have multiple ways to say things. All right, so how are these going here? Each one of these has a second step to it, right? 0.08, what place is that in?
Hundreds.
Hundreds, so you say 8 hundredths, and of course that reduces down.
Oh,
Yeah, you can say 4/50ths, but then it goes 2/25ths.
220.
But you're not getting up, so don't believe me. What about number 12?
10.5.
Yeah, 10 and 5/10, which reduces to 10 and 1/2. Is that cool? Of course, this is in the 10 spot. And the last one, this is in the 100. So it'll be 50 and 5 hundredths. And then what does that reduce to? Good, 50 and 1/20ths. I like it. All right. So one last thing I want to talk about tonight, and then so I got to be careful about this phrase. Obviously, I have a little more to talk about, but then next time we'll talk about 5.2 through 5.4. If you look at your homework sheet, I just want you guys to understand this right now, because people always end up doing way too much homework if I don't say this. I put 5.2 through 5.4 as one assignment, and the page it refers to is on the end of there. Yeah, it's 367. It should be right. If you look at your homework sheet.
Yeah.
So don't do homework from section 5.2. I've made 5.2 through 5.4 homework coming out of this review section on page 367. So 5.2 through 5.4 is just stuff that's all connected to each other. So I'm going to do a lecture over all three of those. So I have one slam bam homework assignment.
So where should we stop? Where should we stop? Where should we stop?
So by next week. we should be-
I'm not sure what you
Where
mean.
should we stop? Like,
You do the assignment on page 367. Yeah.
367.
You just don't do assignment at, some people will do section 5.2, section 5.3, and section 5. I'm like, no. There's one assignment on page 367 that covers those three sections. Just that.
All the way through 5.4.
No.
Oh.
What are we going to talk about next time? You want a quiz next time? What are we talking about Thursday? 5.2 through 5.4. I was just letting you know now that the homework from that section is on one, well, it's 2 pages really, but it's one thing. Right? So there's one last idea I want to talk about from section 5.1. And that's how you compare decimals.
is that was this last?
That was this last one.
So one thing that really helps when you're trying to compare if one decibel is larger than another one is the fact that if I have 0.90, what is that as a fraction?
90
90 over 100.
Yeah. Which reduces to what? 9/10, which is what is a decimal? So we just proved that 0.90 is the same thing as 0.9, and then we should all pretty much know that. I can put as many zeros at the end of a decimal as I want to. It's not going to change the value. Now, if you take science class, you guys still with me? If you take a science class, this number means a little different than that one. This one means that you're more sure about your measurement. So science class is all about measuring things. But math says, okay, you're screwed. That's the same damn number as that is. You with me? But scientists use extra decimal places to show more accuracy. So there is a reason to have that around. The other reason I want to have this around is, if I ask you which one of these is bigger, what you got, Jeff? People will very often tell me that the second one is bigger when that is wrong. They'll see 914, they'll say that's bigger than 92, but I don't see either one of those numbers up here, right? And what you can do to make it the same, you can say, okay, this only has 2 places and this has 3, so let me make that one have 3 also, and now it's just plain as day. 920 is bigger than 914.
You can just add that like that?
That was the purpose of that whole thing there, right? Have I confused other people? So the reason I can add, watch. What decibel does that represent? I mean, what fraction does this represent? 920 over what? Yeah, tens, hundreds, thousands. Doesn't one of those cancel off? So 0.920 is the same thing as 0.92. And if I add more zeros on here, they're just going to be in a deeper spot, and they would all just cancel back off. So I can add as many freaking zeros as I feel like to the end of any decimal. And it will not change the value of it. It will make it easier to look at. And in science, they have a whole other reason for adding zeros on the end of something. But mathematically, it just helps me compare decimals. So this one's bigger. So be careful when they throw something like this at you.
So just pick the smaller number.
The smaller number is bigger. It's the opposite.
Would we be safe just picking the smaller number?
How do you mean? I don't know what you mean.
That's just less, there's
0.8.
there's only 2, that only has 2 spots.
All right, now wait a minute. I want to make sure that I understand what you're saying. The reason this one was bigger is because it's 920 versus 914. Thousandths, right? So if I had put 0.91 versus 0.914, you're not going to say that's bigger because it ain't. Right? 910 is not bigger than 914. 914 is bigger. So
you got a 0.
what's the whole point here? I can't compare these two because they're not out to the same place. So I can't just say that's 91 and that's 914.
Then that's bigger.
Because it just isn't. This is 91 hundredths and this is 914 thousandths. So there's something hidden in there. I can't compare them directly because one of them's been reduced. But if I add a 0 on, now I can just look at that as 910 thousandths versus 914 thousandths. Then the thousandths part doesn't matter when I'm comparing. As long as they're the same thing, I can just compare them now. It's 910 something, 914 something. That one's obviously bigger.
You're going to add a 0 to that. So now
Yeah, it's a good first step. So now they have 3 places each.
Yeah, so that one's bigger.
Careful. What extra thing did I put on this? Negative. So which one's more negative? That's the one that's going to be smaller.
Oh.
That one is more negative, so that one is smaller.
Oh.
So that's another thing. So you got to be careful. So number one, you got to be careful you have the same number of places so you can compare them. And then secondly, you got to be careful. Negatives always reverse the way we look at it. The more negative it is, the smaller it actually is. Okay. So that's the last thing that's in section 5.1. So next time we'll get into 5.2 through 5.4. Big old lecture covering all that. Yes, ma'am.